This is part 2 of lecture 14. In part 1, we have discussed about the basic concepts, the structure of the feedback amplifier circuits, its properties and different features, the merits. And in this part, we will see an example of feedback amplifier and which will help us further clarify our concepts and understanding that we have learned in part 1. So now we'll see an example of negative feedback in amplifier circuits. Of course, there are many examples, but here we pick up one that is we are all very familiar with and also very easy to understand. So circuit that is shown here, this is our well-known circuit. Probably at the first glance it might be a little confusing if it is familiar or not, but if you take a closer look, you will understand what circuit is this. See, this is an op-amp where we apply a signal voltage at the non-inverting input terminal, and at the inverting input terminal we have two resistors, R2 that connects the output to the inverting input terminal, R1 that connects the inverting input terminal to ground. This is our well-known circuit which we call the non-inverting amplifier. So the circuit here is drawn in a slightly different way so that the feedback mechanism become obvious and explicit to us. Now see that R2 and R1, these two resistors, they are basically a series combination and also works like a voltage divider. This works like a voltage divider. And what it is doing, these two resistors together, they are sampling the output voltage V0, and a portion of that voltage will appear across R1, which we indicate as VF. Now at the input side, if you see, we have a signal voltage Vs, and at the non-inverting input terminal, we have this voltage Vf, which is proportional to our output voltage V0. And the difference between Vs and Vf will be taken up by the op-amp, and it will amplify this difference signal. So these two resistors R1 and R2 together, they make our feedback network, because these two resistors together, they are sampling the output voltage and producing a feedback voltage Vf that is mixed with the signal voltage or subtracted from the signal voltage, and the difference signal goes into the op-amp, and op-amp amplifies this difference signal VID and gives us an output voltage. So op-amp itself here is our op-amp itself is the basic amplifier with an open loop gain AOL. So now you see that all the components of the feedback amplifier is now obvious from this circuit. So R1 and R2 together, they make the feedback network, and op-amp is our basic amplifier. VID, which is the difference between Vs and Vf, is our difference signal. Basically, op-amp are fabricated in a way so that it can work as a negative feedback amplifier. So any amplifier constructed with op-amp, they have built in the feedback and they are the negative feedback amplifiers. So op-amp, you see that one of the important component of any feedback amplifier, that it should have a mixer uh, at the input side, a mechanism that will mix the signal voltage with the feedback voltage. For a negative feedback amplifier, it should work in a way that the feedback voltage should be subtracted from the signal voltage, and op-amp is fabricated or designed so that it takes the difference between the two inputs. That is how the op-amps are constructed, that it should take the difference between the two inputs. So that is an important part of any negative feedback amplifier, and op-amp comes with that technology built inside, that it automatically subtracts the the two signal voltages, one the signal voltage and the other is the feedback voltage, and produces the different signal which is then amplifies. So op-amp has built in that technology, so it is easy to construct the negative feedback amplifier using the op-amps. So basically we can say that negative feedback amplifier will have three major components: one, the basic amplifier, the feedback network, and the mixture at the input side, which will mix the signal voltage with the feedback voltage. And op-amp has these two components already built inside: the mixture at the input side and the amplifier, the basic amplifier. And externally we connect these two resistors as the feedback network. So now what are the other features of this op-amp based negative feedback amplifier? The open loop gain is our gain of the basic amplifier, and that we define as V0 by VID. VID is the difference signal. So that is our gain of the basic amplifier. The feedback factor, another important parameter for the feedback amplifier, is the feedback factor, which is defined as the output of the feedback network, which is VF, and that divided by V0. V0, the output voltage, is the input voltage to the feedback network, so that is our feedback factor. Now, what will be the gain with feedback for this op-amp based amplifier? The gain with feedback is defined as V0, the output voltage divided by actual signal voltage Vs, and that we can be approximated to 1 over beta. Now, when this is valid, if this product, the open loop gain or the basic gain of the amplifier, or the gain of the basic amplifier times the feedback factor, is much larger than 1. When this condition is true, the gain with feedback can be given as 1 over beta. Now, we need to verify if this condition is true or not. If this is an ideal op-amp, obviously this will be always true, because ideal op-amp open loop gain is infinite. But what about practical op-amp? As we know, for practical op-amp, they also have very high open loop gain, 10 to the power 5, 10 to the power 6. So even for practical op-amp, in most cases this will be true. The product as a gain of the basic amplifier times the feedback factor will be much larger than 1, and gain with feedback can be approximated as 1 over beta. So now, in order to determine the gain of this feedback amplifier, op-amp based feedback amplifier, we need to determine the feedback factor beta. If you can find out the feedback factor beta, you can determine the gain with feedback. So what is the feedback factor beta? Now the feedback factor is defined as the output of the feedback network, that is Vf divided by V0. And this is just a series combination of R1 and R2. And if you apply the voltage division rule, so Vf by V0 is given by this ratio, and that is what is we call our feedback factor. Now gain with feedback AF is 1 over beta inverse of beta. So you take the inverse of this one, and this then we can express like this, 1 plus R2 by R1. And so this is our well-known gain expression, well-known closed loop gain expression for the non-inverting amplifier. So and see that we have applied a completely different approach using the theory of feedback amplifiers, and we came at exactly the same expression for the gain of this non-inverting amplifier. And what is interesting here to note that the gain of the non-inverting amplifier here, the closed loop gain or the gain of the feedback amplifier, is determined only by the ratio of R1 and R2, that is the components of the feedback network. It does not depend on the open loop gain AOL. You see, that is the main beauty of this expression, that open loop gain can be so, different op-amp can have so many different open loop gains. Not only that, the open loop gain is also a strong function of frequency. It can vary with temperature, it can vary from components to components. So it is so, a fluctuating parameter. You can never have an accurate, precise value for the open loop gain. But when you design the amplifier with the op-amp, the gain of the amplifier becomes independent of the open loop gain, as long as your product A beta is much larger than 1. It depends only by the feedback factor, which is R1 divided by R1 plus R2. And if we take the inverse, and that is our gain expression for the non-inverting amplifier or this op-amp based feedback amplifier.